喂，Hello，好，大家我先讲一下哦。Because the professor is still stuck in the meeting, so please watch this video first, and the professor will come here later. Okay.
Okay, so in this next part of the lecture, I created a PowerPoint set of slides, and just frankly speaking, this part of lecture is borrowed from my other course. It's called. It has a long name. Part of the lecture, I created a PowerPoint set of slides, and just frankly speaking, this part of lecture is borrowed from my other course. It's called. It has a long name. What is it? The name of that course is Analysis and Synthesis, 分析与合成 Analysis and Synthesis of Audio Signals, of Digital Audio Signals. Yeah. So this lecture typically, traditionally should be arranged much later in the semester, but so the corresponding part in the textbook is actually scattered around chapter 8 and chapter 9, right? And so we barely started chapter 4. But this time around, I feel that in practice, we really need to talk about, introduce what is called the discrete Fourier transform as early as possible. So I decided to try this order of teaching in this semester. So in this semester, I will here we are going to introduce two more versions of Fourier transform. So recall that probably in engineering math, you all have learned, I suppose that you all have learned the continuous time Fourier transform. And then we just introduced the discrete time Fourier transform to you. And with that, we also introduced upsampling, downsampling. You now can look at the spectrum, because the spectrum and the signal, two of them form a Fourier transform pair. So there's a one-to-one mapping basically between the two domains. But now let's somewhat confusingly, we are going to introduce two more versions of Fourier transform, and the first one is discrete Fourier transform. Okay. So basically, discrete Fourier transform is applied to a signal of finite length, usually a short length. Let's say the length of in audio, the typical length for us to apply DFT is typically 1,000, 2,000, or even just a few hundred, 256, for example. Okay, and yeah. So in audio in particular, we need to study Fourier transform for a shorter period of time instead of to define our Fourier transform throughout, like from negative infinity to plus infinity. Remember that in the definition of DTFT, the definition itself requires summation from minus infinity to infinity, right? So that's a definition. That's a perfectly fine mathematical definition, but it cannot be computed, right? So that's why we need to again compromise and talk about discrete Fourier transform, which is the basic concept for you to understand. Is pretty simple. Now we just truncate our signal so that it has a finite length, and then apply this version of Fourier transform within that length of 1024 or 2048 or so on, right? Finite length Fourier transform is what DFT means. Discrete Fourier transform means finite length and discrete time Fourier transform. And in audio, it has several applications, such as, for example, coding over speech coding over the internet. We comes into that, voice over IP, and there are some research kind of topics, such as to automatically transcribe music. Let's say you play the piece of piano, and the computer can the computer just figure out immediately which notes are you pressing down on the keyboard. It turns out to be a pretty hard problem, but you understand the idea that the way people play the piano is not stationary, for sure, right? The signal, a lot of time we are interested in non-stationary signals. So the characteristics of signals or the spectral characteristics, 频谱上面的特征啊。The spectral characteristics of signals are constantly changing in time. So in any such kind of either in communication or in speech, in music, or in biomedical signal processing, your heartbeat, for example, is never stationary, right? So to study any non-stationary signal, it makes sense to talk about Fourier transform within a shorter time range of time, right? Within the interval. So that's why that's kind of a motivation, introduction. Why do we need to define a finite length discrete version of Fourier transform? We call it DFT. It's different from DTFT, but there is a relation we talk about later. Okay, so that's the motivation. I mentioned that the sound in general are not stationary, and so is neither is biomedical signals or even in telecommunication. So anytime when we deal with non-stationary signals, we need a more useful version of Fourier transform. And DTFT is not suitable because it requires infinite sum over time. So here is an example, and a piece of music I'll play to you. This is a very famous piece of music. If you know George Gershwin, the composer, American composer in the 20th century. This is his famous work, Rhapsody in Blue. Okay, so now to tell you good news, our new version of Fourier transform, as we'll introduce probably next week formally, is called short-time Fourier transform. So basically, you'll be looking at a piece of signal in time and immediately take the Fourier transform to create a spectrum. And you take the next block of signal in and look at the spectrum over there, and the next block, 2 blocks down the road, and you look at the spectrum over there. So you just convert. So in the end, we convert our one-dimensional signal, which might be infinitely long for sure. That's fine. But by processing them block by block, then for each block we create a short-time spectrum. And so in this representation, we see that the short-time spectrum will be plotted in 2D, where the horizontal axis represents the time goes forward, and the vertical axis represents the frequency. And for every short time, we see every slice of this image represents a spectrum. That is a function of frequency. Okay, so that's the idea. We turn the 1D time domain signal into a 2D image. So that's the idea of short-time Fourier. Pretty easy. And if you look closely, this is great because now we can talk about, if you will, you probably have noticed that in the beginning of this music clip, there is a scale going upward, right? From this note, going all the way to that note, gliding up, only single note. So here you see the corresponding features in the short-time Fourier transform. You can see clear trace of the fundamental frequency increasing over time from the low note to the highest note. And its second harmonic and third harmonic 这边就有一些泛频有一些倍频的结构。Second, third, fourth, all the series of harmonics showing up in the spectrum in short time, right? And we can allow the signal to be non-stationary and in the meanwhile being able to visualize the signal in 2D. Even though the original waveform is a 1D infinitely long signal, but it's beneficial to understand or to analyze, to perceive our signal in 2D because there's a strong reason. The reason why it makes sense to analyze sound in short-time Fourier transform is because really this is how we understand our neural system, our auditory system decodes the sound. Okay. So that's a long story. So actually, our cochlea 跟那个耳瓜and the auditory pathway 那个听觉神经回路 all has a frequency organization. Every place, every neuron encodes a different frequency. So for sure, that also reflects this organization of representation, with time being the horizontal axis, frequency being the vertical axis. This organization is also consistent with 五线谱, with the musical notation, right? You see that from left to right, we have time, right? Time goes forward from left to right, and frequency goes higher from bottom to top, right? So this is exactly what I was showing here, only that this is a short-time Fourier transform. This is a more abstract representation, notation of, so musicians can play the music, right? So they are just 相同的, so they are compatible. The two formats are compatible. So this really makes a lot of sense, right? So hopefully I've motivated you enough that it's really useful to study this new version of Fourier transform, and which converts our time domain signal into a 2D image. But in order to facilitate discussion in these two upcoming, today's lecture and next Monday, we will first talk about the DFT. And there is a relation between DFT and DTFT, okay? And we will discover that very soon. And all right. So in that video clip, which was recorded somewhere in 2021. So while we were still having the pandemics. But the key idea is to motivate you why we need a new version of Fourier transform that works in short time. Okay, we are going to limit our time. Okay, so recall that in DTFT, the definition is we will sum up x of n, we multiply it with e to the minus j omega n to detect how much signal we have at frequency omega, right? And the result is a spectrum, 是一个频谱啊。So the result, summing over all n from minus infinity to infinity. The result is a spectrum. But this spectrum, I say, is not computable. Why not? You cannot compute it because it involves infinite sum, right? So in principle, there's no way to compute this. So in this lecture, we are going to suggest that how about we look at a block of signal, let's say from time 0 to time L minus 1, okay? So that's finitely many samples, and we call it a block, 一个 block. I put it into a vector, right? You can think of it this now. Every block is a column vector. And then we can define a kind of Fourier transform by blocks, okay? So that's today's topic. And why do we need this Fourier transform? One reason is because DTFT is not computable. The second reason is, as I said in that video, all the signals that happen in your life are not stationary. So the feature, for example, for my speech, the features, 那些特征, the features are constantly changing, right? I'm talking, right? So my content is constantly changing, right? So if we handle my speech signal with this kind of Fourier transform, then we are not respecting the fact that the property of the signal itself, themselves, they are constantly changing. So we might want to study the signal one block after another, just to study the short time properties. How short is short is up to your domain knowledge, but we do, hopefully I've motivated you enough that we do need another kind of Fourier transform which works in short time so that we can understand music automatically. We can analyze speech automatically. So basically all this automatic speech recognition and music retrieval, all applications depend on this new version of Fourier transform that we are going to introduce today. Okay? 好. So new version of Fourier transform, and this new version of Fourier transform is called discrete Fourier transform. The discrete Fourier transform. That's a new, or DFT. Okay? This is a new thing we're going to learn. Particularly, we're also going to talk about FFT. So many of you might have heard of this a lot, fast Fourier transform. So the take-home message, okay, for you to just understand is what we call fast Fourier transform is nothing but a fast implementation of DFT. Fast Fourier transform is simply a fast version of DFT. FFT is DFT being fast. Okay, so that's it. Hopefully this is easy enough to understand. Okay, take-home message. FFT. What is FFT? FFT is a fast version of DFT. But then, what is DFT? Why do we call it discrete Fourier transform? And what is its relation with DTFT? Okay. Yeah, so this is what we're going to introduce. And also we are going to talk about an application of fast Fourier transform. Because it is fast, it helps us accelerate FIR filtering, finite impulse response. Right? We have designed low-pass filter, for example, high-pass filters, let's say by the window method, right? So that gives you an FIR filter. And it turns out that it's faster to process your signal. Then with the filter, it's faster to process the signal in the frequency domain than directly in the time domain. Directly in the time domain, what you need to perform is convolution. We need to convolve our signal that comes in with the impulse response, convolution, right? And that produces the output. But it turns out that convolution itself in the time domain is less efficient. It's more efficient to do it in the frequency domain, as we will just explain why. Okay? So that's today's topic, DFT, FFT, and acceleration of FIR through FFT, working in the frequency domain. So I can just skip this. So basically, DFT, FFT, and acceleration. So first thing first, okay? What is DFT? The definition starts with the assumption that we obtain a block of signal, okay? So here is a bit about the notations. if we assume that we use the bold font, 粗体字, the bold font to represent vectors, 好吧？粗体字就是向量啊。We use the bold font to represent vectors. So let's say we have a block of signal S that contains L points, L being the length of the block. So S can be denoted by S0, S1, all the way to the last sample. And in total, we have L samples right here. In total, we have L samples. So now with that, we can define the DFT, the discrete Fourier transform of small s, the signal, is a spectrum. The result is, again, a spectrum, but is defined on discrete frequencies. Okay? So here, again, we use big S to denote frequency domain, small s for time, big S for frequency. Okay? Big S, and there is a big S. Yeah, not big. I need to watch for my pronunciation. Big S. No. Big S, uppercase S, right? So K, here the index K is a frequency index. Okay? And K takes values on integers. Okay? K also goes from 0 to L minus 1. Okay? So we start with the time, in the time domain with L samples, L points, but the result gives us a spectrum of L frequencies. So it's an L-dimensional to L-dimensional transformation. It's a transformation from an L-dimensional vector space to another L-dimensional vector space. But otherwise, the definition looks very similar to DTFT, right? This idea is similar. We basically multiply our signal in the time domain with the complex exponential of frequency. So here you can say the frequency omega for the kth spectral line. K, sometimes I call it spectral line. Spectral line index. So the frequency number K equals to K times 2 pi divided by L, where L is the length of the block in the time domain. Okay. So if you will, you can also call 2 pi divided by L as, call it fundamental frequency. So it's a frequency where the period is L, right? When the period, 周期是 L, when the period is L, of course the frequency, the angular frequency is 2 pi divided by L, right? So here, the kth frequency, the kth frequency is K times the fundamental frequency. But otherwise, the definition is really, really similar to DTFT. We have signal in the time domain right here, and we multiply it with a complex exponential so as to project the signal to the frequency domain, onto the frequency domain. Right? This is a projection again. And the result is a spectral line at K, K is the frequency index. Okay, so that's a definition. That's a definition. So far, so good? Simply a mathematical definition. The next question is, why do we call this a discrete Fourier transform? We have so many versions, discrete time Fourier transform, to emphasize that it's not continuous time, right? In that case, discrete time Fourier transform is to emphasize that this kind of Fourier transform is not continuous time, but discrete time, adjective, 形容词. But now we have a new version called discrete Fourier transform. Why? Why is it called discrete FT? And the answer is because discrete Fourier transform is DTFT sampled in frequency. Now we have a sampling in the frequency. Or to be more exact, if I say this is the definition on the previous slide, okay, that's the definition, our definition, then this can be thought of as the DTFT. I should have written S of EJ omega, okay, to be more consistent with the notation of the textbook. But you know the spectrum. DTFT. So DFT is DTFT sampled in frequency. In that we evaluate, now if you evaluate DTFT at this very frequency, that gives you S of K. Should I say that again? Okay, you compute the DTFT in the good old-fashioned right here using this method. But then when we evaluate DTFT at exactly this frequency, K times the fundamental frequency, that gives you the kth component of DFT. Or in short, DFT is DTFT sampled in the frequency domain. You can even draw an image, okay? So we know that DTFT is a spectrum and it has a period of 2 pi, right? Hopefully you all understand that. But now you should understand that. So let's draw the unit circle again. So we've talked about DTFT is Z transform evaluated on the unit circle, right? We mentioned that so many times by now, okay? So if this is real of Z, imaginary part of Z, and if this is the unit circle that we often look at, then DFT is DTFT. We know that, by now we know that DFT is DTFT, no, I'm sorry, DTFT is Z transform evaluated on the unit circle, right? But now, what we're doing here is to cut pizza on the unit circle, okay? So we're going to focus on discrete frequencies points, such as frequency 0 right here, maybe. Let's use this as an example. Let's say if we cut the unit circle into 8 equal portions, then essentially then we have a DFT of length 8. Okay, DFT, if this is an example of L equals to 8, then DFT, what it does is to calculate the spectrum, but only at these 8 discrete frequencies. So that's, maybe I shouldn't use the cross sign, because this is not about the pole of a system. Okay, let me use another symbol. Let's say just a circle. Okay, just some kind of dot. We are separating the unit circle into 8 equal parts. So DFT is DTFT evaluated on discrete frequencies, on equally spaced frequencies. Depending on, and then now the spacing here, really, you can see the spacing here. The spacing here is 2 pi divided by 8. We divide the entire frequency range into 8 equal portions, right? And then we can just evaluate DTFT at these exact 8 places, and that gives you the discrete Fourier transform. And that's the reason why it is called discrete Fourier transform, because now in the frequency domain, importantly, now in the frequency domain, the spectrum is also discretized. 也被离散化了. The spectrum is also discretized in the frequency domain. All right? The spectrum is also discretized, and that's why we call this DFT. Yeah. And the next slide here, I want to introduce to you that we can have a matrix representation for DFT. As I mentioned, DFT starts with a block of length L, and it gives you L spectral lines. Okay, so it's an L dimension to L dimensional linear transformation. You can easily verify that, of course, DFT is linear. It's a linear transformation. Okay, in linear, and it turns out it's also invertible. Okay, linear and invertible transformation. So it has we know that every linear transformation has a matrix representation, right? Every linear transformation from finitely many-dimensional space, from a space of finite dimension to a finite dimensional space, is can be represented by a matrix. Okay, so let's now particularly look at the matrix representation using the standard basis. Okay, so here is the result. This is the matrix. Okay, this is a matrix of L by L, and we call it F, referring to the Fourier transform. Okay, so it's a version of Fourier transform. So this matrix F, if you look at it, you see that it's first of all it is symmetric. Okay, F transpose equals to F. Did you notice, right? And then secondly, there is a factor, a complex values factor right here we need to talk about. There's a W factor right here, which denotes this e to the minus j 2 pi divided by L. Okay, there is a factor W right here. But otherwise, the organization is pretty, is very well organized. The matrix, if you look at, for this matrix, if you look at the column, or look at the row, yeah, it doesn't matter because it is symmetric. So let's say if we look at the row, then we have the first row is all 1, the second row is W squared, W third, and so on, okay? And the last term is this, right? That's one row. The next row is also a geometric sequence, okay? But with a factor of W squared. Okay, so that's the organization. So of course, then with that, the last row is W to the L minus 1. That's the ratio for this row. So each row is a geometric sequence. Okay, some people call each row a complex, a spiral wave. Let me write it down. Each row can be called a spiral wave. Why? If you consider a row being itself a block, and actually you can very well say that every row is itself is a signal, but every row being a signal, it has a real part and imaginary part. It's complex valued, right? But otherwise, this signal has a fixed frequency. So here I'm going to plot the signal in 3D because it has a real part and imaginary part. So we start with 1, right, which is a real number. That's for example, that's the first element. And the second element is going to go what? Does it go counterclockwise or clockwise? It goes clockwise because there's a minus sign right here. It seems. Okay, so it goes clockwise. For the next sample, we have a imaginary part. So it probably go. How do I draw this? I'm having a trouble to draw this. Yeah. It goes this way, clockwise, when time proceeds. As time is proceeding, if you plot the real part, imaginary part, you get a spiral. You get a spiral-shaped trajectory, 一个这样的轨迹啊， you get a spiral-shaped trajectory like that, and it is periodic. Okay, so we call this every row can be thought of as a spiral wave signal at a particular frequency. And what is that frequency? The frequency is if this is the mth row. So first row, second row, third row. So for the mth row, the frequency is, can anybody tell me? For the mth row, the frequency should be m minus 1 times the fundamental frequency. That's the frequency of the frequency of the spiral wave. And this is important, okay? All right, so imagine this is DC term, all one, DC, right? So the first row is all one with 0 frequency, DC component. The second row corresponds to the fundamental frequency wave, the wave at fundamental frequency. And the third row is 2 times that frequency. There's a factor of 2 because of this exponent. 2, 4, 6, 8, and so on. See, right? So another spiral wave, but with double frequency and triple frequency and so on. So the last row has a frequency of L-1 times the fundamental frequency. Every row is a spiral wave. Can we see that? Okay? Every row is a spiral wave that rotates faster and faster around that time axis. Okay? So that's why these waves, these signals are being complex values. The complex exponential signals are sometimes called spiral waves. But why is this important? Note that now we are going to multiply. You can verify that when we multiply this matrix with any given signal, any given block of signal, we multiply this matrix with the signal, then that gives us a vector, right? If small s is L times 1 is a column vector. And now we multiply it from the left with the matrix F, which is a square matrix. Okay? What's the result? The result, big S. Big S is also a column vector, right? It's an L dimension to O dimensional linear transformation. But at the same time, what does it mean to perform matrix multiplication? There are different ways to interpret that, okay? When we multiply a vector with a square matrix, that means one way to look at it is to see that what we are doing is to perform inner products. We're performing inner product of every row with our signal, right? Matrix multiplication, right? So we are basically performing inner product of each row separately with our signal, which is a column vector. And the result is put to the left-hand side of the equation, right? The result is put to the left-hand side of the equation being a column vector starting with the lowest frequency component, the fundamental frequency component, and the highest frequency component in the end. So it's a linear transformation is inner product, which can be thought of as projection. So basically, this is a projecting from time domain to the frequency domain. And each component tells us how much of the signal we have at separate frequencies, starting with DC, ending with the highest frequency. Okay? So that's the way we look at this matrix representation of DFT. Okay? I hope that this is a useful way of looking at the transform. It's a linear transformation. Now, any comment right here? Okay. So that's the direct definition of DFT, which can be represented by a square matrix. Square matrix inner products. Okay. Now, so basically here, we can have some summary right here. Okay. DFT is a projection onto a new coordinate system. Okay? Let's say our signal has L samples in the time domain. So that's a time domain is a coordinate system. 是一个坐标系啊. Being L, we have L dimensions. Each sample can take values, real or complex. But anyway, every sample is one dimension. And in total, we have L dimensions. Okay, so it's a coordinate system. This is how we represent the signal in time. But after multiplying with the matrix, we go from time domain to the frequency domain. And this essentially is a change of coordinate, change of basis. Change of basis. It's a change of basis, and now the new basis consists of rows. Now that's one row vector, the second row vector. These row vectors are the new basis vectors, okay? Each of them, roughly speaking. Roughly speaking, that's the case. Okay? So I have a summary right here for you. So let's go through the notes. Each row represents a basis vector, 一个基底向量啊。Basis vector. And further, you can check that they are mutually what? Anyone want to take a guess? They are mutually orthogonal. Orthogonal, yeah. They're mutually orthogonal, meaning that if you take one row and the next row and perform inner products, okay, it's going to be 0. Yeah. So if we call, let's say, if we call this row V, actually, you know what? Since this is symmetric, it's easier if we consider columns. Yeah. It's easier if we consider columns. If we call S, the F matrix, if we just organize it and call the first column V1, maybe V0, okay? The second column V1 and so on, all the way to VL minus 1. So we have a square matrix of L columns, okay? So I'm saying that being orthogonal means that if you take any two columns, two different columns, and perform inner products, say V, I, Vj, perform inner products. Perform inner products. If you just do that, that means we take further. We need to be careful about this, okay? When we perform inner product, we need to take the Vi Hermitian with Vj. Do we know what is a Hermitian? Hermitian is transpose then conjugate. Okay? That's a definition of complex value of inner product for complex valued vectors. 复数的向量 complex valued vectors. If you have two of them and you perform inner product, that means you take the Hermitian of one of them and otherwise perform matrix product. Is delta L times delta Ij, which means that equals to L if I is J, but is otherwise 0 if I is not equal to J. Orthogonal vectors right here. So I'm not going to prove that, so it's rather straightforward to show it by yourself if you're interested, okay? DFT being organized in this way turns out that all the columns are mutually orthogonal. Okay. Any comments right here? Did I remember this correct? Yeah. I hope I remember this correctly. Okay. Some people put the Hermitian for Vj Hermitian Vi. Yeah, it doesn't really matter. It's just a matter of notation, of convention. 这是一个习惯问题啊。Right. But importantly, one of them needs to be conjugated when we perform inner product of two complex valued vectors. One of them needs to be conjugated. Turns out that all the columns are orthogonal. So this is nice. Yeah. You know that orthogonal is a virtue. 是一种道德啊。For a basis, when we have a orthogonal basis for any space, it's very convenient. Like XYZ, orthogonal, right? Mutually perpendicular. That's the meaning. So you can think of a Fourier transform as consisting of column vectors, and all of them act like XYZ. They're orthogonal. Okay, they're orthogonal. So when you perform decomposition, that comes out convenient. They are convenient. Okay? When you perform change of faces, that is convenient. Okay, so this is the note number one for my slide right here. Note number one, the columns are basis vectors and they're orthogonal. And we basically calculate their inner product with our signal with the signal right here. The signal is a column vector, and our basis vectors are all column vectors, right? So what happens when we perform inner product? So what's happening right here is that f times s equals to basically complex conjugate. Let me think of this more clearly. V0 transpose, I need to be careful, okay? V0 transpose S, V1 transpose S, and so on. That's a result. VL minus 1, the last one transpose S. So basically, we are calculating the inner product of these basis vectors with our signal. Or to be more exact, we are calculating our basis vectors conjugate, and we perform inner product of them with our signal. Okay, that's what exactly is going on right here. Last one, conjugate with S. Okay. So what is Fourier transform? Okay, let me stop right here. Pause for a moment. Let me pause for a moment. When we perform matrix multiplication with a vector, we take every row separately and just multiply them element-wise with our signal and then sum up, right? So that essentially that's what's going on here is an inner product. But as I mentioned, that when everything is complex value right here, we need to be careful. One of them needs to be conjugated. Okay? So in this case, it seems to me that when we want to say that Fourier transform is to perform inner product, is equivalent to inner product. When we say Fourier transform is equivalent to inner product, we need to be sure that the basis vectors right here need to be conjugated. Okay? It seems to me that this is the correct way of saying it. Where W is given to you. Okay, where W is equal to e to the minus j 2 pi divided by L. This is a common factor. And so I will let you, so later in your life you can figure out where to conjugate so that we stick to we adhere to the definition of inner product. But I just conceptually, Fourier transform really is an action of calculating the inner product of our signal with the basis vectors, with all those spiral waves. You calculate your signal's inner product with the spiral waves separately. Each of them is a spiral wave, as I previously mentioned, right? So that's the way to go from time domain to frequency domain in this case. Performing inner product with your set of spiral waves, and these spiral waves are mutually orthogonal. So the change of basis is projection is inner product. Everything is can be summarized by this matrix representation. It tells us a lot of information. Okay, so this is what I want to share with you. So in short, Fourier transform, what is going on right here? Fourier transform is a change of basis. Projection, a change of basis from time to frequency. Okay, start with time domain right here, end with frequency domain spectral lines after the transformation. Okay, and how about the computation load? So in this next page, now we understand this is a matrix representation of DFT. The question is, how many multiplications does it take to finish the computation? Okay. If we use this direct definition of DFT, how many multiplications does it take to finish the computation? We don't care about summation so much. Okay, summation is easier, but how about multiplication? So if you will, for example, 1 times S0, you can argue that it's not a multiplication. 1 multiplied by anything doesn't change anything, right? But generally, when the matrix is large enough, generally it's dominated by here, this portion of the matrix, where each factor right here is a complex number in general. So we have, let's say, roughly speaking, the computation load is in the order of L squared. Can we agree on that? Because we multiply, multiplication, 1 multiplication, 2 multiplications, last multiplication for this row, and then we change the next row, 1 multiplication right here, 2nd multiplication right there, and last multiplication right there. So roughly speaking, the computation load is in the order of L squared, or to be exact, maybe it's L minus 1 times L minus 1. Maybe that's so many multiplications to complete our calculation of DFT. Okay, so the answer is the computation load. Direct computation right here involves roughly speaking in the order of L squared, so many multiplications. Maybe a little less. Okay, maybe a little less because many factors right here are simply 1. Okay, maybe a little less, but roughly speaking, it's in the order of L squared. So historically, it becomes a kind of a barrier for DFT to become useful. L squared is a lot of multiplication. Okay. So people ask whether or not there is a way. Is there any way we can reduce the computation load? And the answer finally is FFT. So we'll come back to this after the break. Okay, let's take a 10-minute break.3次方式我是有搞错。对，需要到平方吗？我来看一下，这个一项的话，对，一项好像是一项就是 L 啊，呀，没问题，就要想清楚了，对，不会啊。 Hello. Let's continue, right? Welcome back to DSP. Welcome back to DSP, right? Okay, so many of you came up to me to ask about spiral waves. First of all, what's going on, right? So here, let me explain a little more, okay? So in this figure, in this figure, wait, what happened to my? Full screen, not full screen. What happened to my? 怎么那个？哦，再跑到下面去，奇怪，怎么跑到下面去？好，I was looking for 这个东西啊，不知道为什么跑到下面去。So the spiral wave right here. So in this figure, I'm trying to show you how to imagine a row. Okay. So now I invite you to imagine that a row. Every row is a signal. So before we even talk about performing inner product, let's imagine every row itself is a signal of length L. Okay. So this is going to be its first sample, second sample, third sample, and so on. Every row is a signal. And I was trying to share with you that every row can be thought of as a periodic signal with frequency, with a frequency of k times the fundamental frequency. Okay? Every row is a signal of integer multiple times the fundamental frequency. And the way to look at it is, first of all, note that it has every signal has real part and imaginary part. So if we want to plot this signal, we need to use 3 dimensions, right? Real part, imaginary part versus time. Time goes that way, okay? So now, as I'm standing on the stage, let's imagine that my left hand right here is the time axis, okay? So we have discrete time signal. So every step is going one step further in time, right? Okay. So what's going on here is that the first sample is just like pointing to my right, because it has only the real part. The first sample is 1, right? First sample is 1. So it has only the real part. But how about the next sample, W right here? W is this. E to the minus j 2 pi divided by L, right? So what is that? This is going in which direction around the clock? It's going, actually, I might have got it wrong. I might have said it wrong. It's clockwise. So this is like going one step. Each step is going clockwise by by an angle, and then going just rotate further by that angle, and then rotate further by that angle. So in there it has a spiral. I don't know. There is a spiral shape that goes this way. Goes this way. Okay. Yeah. Now think about this. Okay, spiral waves. And some people also have a comment that about the definition of inner product. Okay, I said one of them needs to be transposed and then conjugated. Here, H Hermitian means transpose then conjugate, or conjugate transpose. And conjugate conjugate is important. Okay, and we need to conjugate one of them. Otherwise, inner product, we have a problem, okay? Otherwise, when we take the inner product of one vector with itself, when I equals to j, it all comes down to this requirement. When I equals to j, that means we're calculating the inner product of one row or one vector with itself when I equals to j. And the result needs to be real. If I remember correctly, I think I remember correctly, okay? For any vector, when we calculate its inner product with itself, that should equal to norm square, right? And norm square is real. Actually, it's non-negative, right? So in order to satisfy that requirement, one of them, in general, when we calculate the inner product of two vectors, one of them needs to be conjugated. Okay, now here in my habit is to conjugate the first one. In other textbooks, maybe, you can check. Probably in other textbooks, now I remember my definition might not be consistent. Or let me put a question mark. In other textbooks, the definition might be Vj Hermitian Vi. Doesn't really matter. Okay, one of them needs to be conjugated so that when we perform inner product of one vector with itself, the result is real. That's the requirement to satisfy. Okay. So that's some tiny detail right here. But when we step back and just look from afar, Fourier transform, more important message is that it's a linear transformation. All the rows are orthogonal. So basically, we can think of Fourier transform as projection, as change of basis using an orthogonal basis as the new coordinate system. Okay, so that's the concept we need to just hold on. Hold on to those concepts, and you should be fine. Right? Okay, but anyway, so I was asking the question in the end of the last hour. We were asking a question regarding computation load. The computation load appears to be in the order of L squared. It appears to be in the order of L squared because now we have this matrix representation. It tells us that when we perform inner product using the direct definition, the computation load seems to be in the order of L squared. There are so many multiplications that need to be performed to complete one block of Fourier transform. Okay? Is there any way we can reduce the computation load? Is there any way we can make it faster? We can accelerate the process. And it turns out that in the year of 1965, 1965, Cooley and Chucky, by these two authors, discovered an algorithm for calculating what they call complex Fourier series. And they have reduced successfully. They reduced the computation load successfully from L squared to L log 2L. Okay, so that's the kind of the result, the highlight. The computation load has been reduced from L squared to L log 2L, and just because of that, this algorithm is often named as one of the 10 most important algorithms in history. We mean in history. Okay, what are other candidates? I remember quicksort might be, merge sort or quicksort. Is also on top 10. But FFT is definitely top 10. Okay, top 10 discovery in computation for the 20th century. You can name it. And another note is that, as we'll see in a moment, often it's a good habit, okay, to use a power of 2, let's say 2 to the 10th power, or 1024, as your FFT length. Okay, usually it's a good habit to set the length, the block length in our case, set that as a power of 2. Let's say 1024 is a good candidate, or 512, 512, 256, and so on. 2 to a power of 2 is usually the most efficient way to implement for FFT to happen. Now, the reason why. Now let's look at this figure. Why do we recommend the length of FFT to be a power of 2? So in this case, taking the length of 16, for example. So here, in this example, L is 16. And our signal x now goes from x0 to x15 on your far left, on the very left of this diagram. Okay? So we start with our signal in the time domain, small x for time. So this is in the time domain. But now, when you look at this flow, things go from left to right, okay? All the arrows go from left to right. Do I see arrows right here? Okay? Yeah, we see arrows. All the arrows go from left to right. And finally, all the way to the right. Okay? All the way to the right. But otherwise, what do you notice? You notice that, and we claim that, okay, I'm not going to prove this in class, but we claim that on the right, this is big X, okay? So we go from time domain all the way, the end product right here is already in the frequency domain, okay? This is frequency domain with big X. All the spectral lines. 16 samples in time to your left, 16 spectral lines to your right. We are already in the frequency domain in the end. Okay? So the flow go from left to right, one direction. But otherwise, what do you notice? Do you notice a crossing, right? Crisscrossing of the path. So we have this 交叉, crisscrossing in this structure. We have crisscrossing right here, right here, right here. It's a crossing. And also crossing right here, right here. Crossing, 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 crossing. And then in the end, in the last stage, it seems that in the last stage we have crossing like that. Okay? So that's one first thing to notice. We have crossings. Things to notice. To notice. First is the crossing. Secondly, I want to say this idea is to divide and conquer. Okay, is to divide and conquer. So note that here's should I call it stage 1, stage 2, stage 3, and stage 4. So when we go from one stage to the next stage, it appears that now we are dividing our task into subtasks. There's a self-similarity in here. 自我的相似性, self-similarity, if you will. Okay? So it appears that, for example, look at this. Here, that's a unit. And this is also another unit. It seems that we are dividing our task into 2 subunits. Each of them has is an 8-point to 8-point transformation. Okay? After crossing. So still, but otherwise, and further, now we divide each length 8 unit into, we divide the task into further into 2 subtasks of length 4. We start with a length of 16, but then we divide the task into, we break the task into 2 units of length 8, right? And then further, we divide that each length 8 units further into 2 subtasks of length 4, right here. And eventually, we end up with length 2 to the far right. And we do that by dividing each unit of length 4 right here in stage 3 further into 2 subtasks of length 2. Okay? Now, so that's what's happening. Okay? And then seriously, the crossing is just to connect the path. Okay? And in each one, when we have like 2 branches flowing into one node, that again that means summation. So this same principle of drawing the diagram is still true right there. So each time we see a node, each time we see 2 branches flowing into the same node, that means summation. Okay, we still apply the same principle when we are drawing this flow. Okay, branches flowing into the same node means summation. But otherwise, you can just after a detailed look, where do we have multiplications? That becomes the question. Okay, so here is just summation, but all the multiplications in this plot happens right here. Whenever we see the multiplier is right here, okay? These are the only place we need to perform multiplication. Multiplication by different factors, okay? So each multiplier right here is associated with exactly how to multiply them, okay? Here, so in right here, we multiply with a factor of W, for example, a factor of, we just indicate the multiplication factor right here next to the multiplier. Okay, that's the way we read this plot. We have a multiplier right here, a symbol right there, and nearby you find a factor, for example, W of 4 times 0 sub 16, or here is an example, W5 5 times 1, 16. Okay, so this needs some explanation. First of all, on top, the index right here. Here, these really are the exponent. 是几次方啊, really, this on top. The superscript, 上标, the superscripts tells us that they are the exponents. 确实就是几次方, exponent. W raised to the power of 5 times 1. Okay, really, these are the exponent. But then, what is W? The subscript 16 here indicate W16 is this factor, e to the j minus 2 pi divided by 16. That's the subscript. Okay, and later in the flow, you also find W8, W4, the subscripts 下标. So similarly, W8 is e to the minus j 2 pi divided by 8. Now, these are the factors that can be pre-computed. 可以预先计算. These are the factors that can be pre-computed. Let me just erase this. I want to erase. How do I erase? Right here. Let me write one more factor right here. W4 is e to the minus j 2 pi divided by 4. And these are factors that can be pre-computed. And all their powers, okay? Okay, is that clear? 会不会太小? Okay, can you really see it? Yeah. So we have the multipliers. Right here, we have a stack of multipliers. And a stack of multipliers and another stack of multipliers. But otherwise, we know exactly. It seems that the author, Cooley and Tukey, they discovered how exactly to place the multipliers, how exactly these multipliers should be. So, and they are very well organized. W012, W16 to the specified power, W16 to the specified power right here. They are very well organized. W16 right here, W8 right here, okay, W4 right here, and so on. Okay, so that's somehow these two authors discovered a way to organize the multiplications like this with crossings, summation right here, and multiplier right there. Okay, and in the end, here, in the last stage, in the final stage, we just need to sum up. Yeah. The last stage does not even require us to perform multiplication. Okay, surprisingly. Okay. Okay, so I was going to summarize our observations. 这些观察. We observe that there is crossing of path. We also observe that we just successfully 不断地 successfully break computation into subunits. Into subunits. So if you do that, no wonder how many stages we have. If we start with 16, a block of 16 samples, and we are going to successively break our task into subunits, divide by 2, okay? For each further stage, we divide our task by 2. So in the end, because we start with a length of 16, then one stage goes to 8, next stage go to 4. Third stage already we go to units of length 2. And that's why we have exactly log 2 of 12 of 16. We have so many stages. In this structure, we have 4 stages. And why 4? 4 is log 2, 16. Okay? Four. So third observation is that the number of stages equals to log 2 of L. And in this case is log 2 of 16 equals to 4. We have in total 4 stages. After 4 stages, we have simplified our task into unit of 2, into 8 units of 2. So that's a structure. That's a structure. And how many multiplications do we have on this flow? Now we can answer this question. How many multiplications do we need to perform? In each stage, we perform 16 multiplications, right? In each stage, at each stage, we perform 16 multiplications right here, 16 multiplication right here, 16 multiplication right here. Theoretically, we also perform 16 multiplication, but now the multipliers are all ones, okay? So how many multiplications do we need to perform in total? So it seems that now we can answer that the number of multiplications is equal to L being 16 times log 2 of L. And it seems that there's a -1. Because in the final stage, it turns out that we don't need to perform multiplication. We just need to sum. We just need to perform summation. And let me add a 5th note. My memory, if I remember correctly, or maybe in the crossing, is really, I remember when we have a path pointing up, that means -1, okay? Otherwise, the plot wouldn't make sense, okay? So let me just put a question mark right here. Please, you're very interested in the details. Each time when we have the arrow pointing up, that means multiply with -1, okay? I remember we need this definition. Otherwise, the last stage wouldn't make sense, okay? Otherwise, the last stage does not make sense to me. Let me put a question mark. Just, if I understand correctly, okay, all the paths, all the arrows that point up, those need to be, we need to change sign for those in there, okay? Now there's a change of sign from plus to minus, okay, right there, okay? I apologize for not remembering the fact, okay? But otherwise, the last stage would not make sense to me. You cannot perform summation right here, and they appear to be the same. That shouldn't be the case. So one of the arrows right here got to be a change of sign, probably this one. There's a change of sign right here. I argue that's what I remember. Okay, right. But the important thing is that it seems that even with the change of sign, the last stage, it seems that the last stage does not require multiplication. It's just sum or difference. summing right here, differencing right there. Yeah. So the last stage is the most simple. Take the sum, take the difference. Okay. So that's a structure. That's one of the many equivalent structures of FFT. Okay. So back to my title right here. I need to share with you. If this is surprisingly beautiful, okay, to you, congratulations. We have many equivalent implementations. Okay, this is one of many equivalent structures of FFT, and all of them involve a computation load which is much reduced. Now the computation load becomes L times basically order of L times log 2L. Okay, that's an important fact to understand. Okay, the computation load is L log 2L. Okay. Questions so far? Any comment? Anything that needs more explanation? Is there anything that's not clear? Yes, please. 对. Okay, so let me explain that in Chinese and I'll explain again in English. Okay, 我的意思说，这边有些箭头是这样子指上去的，这些都这样指上去，然后有些是指下来的。直的就是直的，没问题啊。但是我印象中有哪一个方向的，好像是 either 是往上还是往下 ，I may be wrong, maybe 是往下必须要乘一个负号，因为如果不乘的话，最后这个不 make sense 因为这个话是完全相同的 ，sum 跟 sum 所以可能是好像往下的要加负号了我现在想往上，所以可能好像是我现在要去好像是往下。My memory is fading, but to be honest, one of them got to be involved a change of sign. Okay, so let me explain this in English again. Okay? So the question was, what's going on? What do you mean? An arrow pointing up involves a change of sign. So I mean that my memory is fading. I apologize for that, but it's either all the arrows pointing up or all the arrows pointing down need to involve a change of sign. Please check, okay? So yeah, I remember one of them, either all the arrows pointing this way, pointing downward, or it's either or. Should I say X or? Okay, yeah. Or all the arrows pointing up needs to be involve a change of sign. Otherwise, the last stage would not make sense. Otherwise, the last stage does not make sense. If all of them involve just summation, branches flowing into the node, summation, then this node should be equal to this node. The last stage will not make sense without making one of them, without changing the sign of one of the path. 如果不改的话, it doesn't make sense. Okay? All right. Please check. I apologize for not remember which one should be the change of sign. Okay, but it appears to me that one of them need to change sign. Right. So that's what I remember. 对。Yeah. Okay. So. That's a good question. The question is, now the exponent here seems to be 7.0, right? It's not point. That's 7 times 0. That dot right there is 7 times 0. 2 times 1. 2 times 1, okay? It's not fractional point, 并不是小数点Yeah. Not fractional point, but 3 multiplied by 1. That answer, that's a clarification. We need to clarify that. Thanks for pointing out the question. So this is just one of many equivalent structures of FT. And let me see how many slides do I have. I have more slides to cover than I could finish in 15 minutes, I'm afraid. Let me continue. I need to rush. Okay, we need to catch up. So next slide is inverse Fourier transform. Okay, yeah, inverse Fourier transform. And it should be easy. Let me just quickly go through this, yeah, because I really do want to get to the part of FIR acceleration. Okay, I hope that I really hope that will be our last topic of the entire semester. Okay, yeah, yeah. But before we jump into the FIR acceleration, let me just tell you that inverse FFT and FFT has this very simple formula. Okay, inverse FFT, you can verify that it is equal to F conjugate with a normalization factor. And this has something to do with orthogonality. We have mentioned that all the rows or all the columns are mutually orthogonal. Therefore, when you multiply F with F conjugate, it becomes diagonal. Okay? And therefore, inverse Fourier transform has the same structure, same appearance. Okay, only with a so this is a summary. If forward Fourier transform goes from time domain to frequency domain like that, the inverse Fourier transform goes from the frequency domain to the time domain like this, with a normalization factor and all the v vectors right here, all the the factor v right here is equal to W conjugate. And W conjugate is W inverse. Yeah. So the structure will be the same. Okay. Forward transform. This is some forward transform. This is inverse transform. Inverse transform goes from the frequency domain right here to the time domain right here. Yeah. So what's the implication? That means that if you know how to implement DFT in a fast way, if you know that, then you know how to implement inverse DFT also the same way. Okay? Because the structure right here is really the same thing. The only difference is that now every V here is W conjugate. Okay? So that being said, quickly, when we go back to the flow here, just change W to V, then you have an implementation of inverse FFT. Okay? So same structure, just change W to V, then you have an implementation of inverse transform, which goes from frequency domain to time domain. Computation load will be exactly the same. Okay? So don't worry about that. Okay? The computation load will be the same. The structure will also be the same. Okay? And okay, yeah. So should I enter the last topic, the final topic? Okay, how would be an application of FFT? Okay, FFT can be used to process our signal in the frequency domain. Okay, so previously when we talk about filtering, everything is in the time domain. We use a difference equation, right? The entire semester I've been emphasizing that when we implement a filter, we design a filter, the end result is a difference equation. I've been emphasizing that for IRR filter, for Butterworth filter designed using bilinear transform. The result, what you get? You get a difference equation which works in the time domain. But it turns out that we also talk about FIR design, right? FIR design, and by now, if you remember, when we talk about this, we have the same filter specification. We're designing a low-pass filter with the same passband, cutoff frequency somewhere, with transition width requirements somewhere, and also the ripple and so on. So often you will find that then when we compare FIR versus IIR, which one is better? That's a question. Yeah, which one is better? Let's recall that for FIR, we talk about the advantage is we can design linear phase, right? Phase response can be linear, so group delay can be what? Can be constant, okay? So group delay is constant, and that's good, okay? Yeah. But IIR, what's good about IIR? Usually the IIR, the order of your IIR filter can be lower than FIR with the same spec. Okay? So IIR, usually the order is lower. So that means that if we use a difference equation on the order, how many terms do we have? Including using the direct form implementation. The order is important because order means computation load. The lower the merrier, the lower the better. So in that regard, IIR is a better choice. Okay? FIR is better in having constant group delay. This can be guaranteed. So that's the advantage for FIR. But IIR usually has a lower order. Okay? But it turns out that now with this topic, the final topic, turns out that FIR can be attractive. 其实还是有吸引力的。FIR can be appealing once it's accelerated by FFT. Then it can be competitive, can be as good as IIR or even better. Okay, so practically in my life, I use FIR more than I use IIR. Okay, so that's why we need this. This is a very nice final topic for the entire semester to reconsider FIR as a good candidate. Okay, we can reduce the computation load of FIR using FFT. Okay, so that's a motivation. So in this final topic, here the idea, the overall flow you need to be kind of aware of is to go to frequency domain. So how does that happen? For every input right here, we would use a window to take a block of our signal. Let's say using the rectangular window. Okay, for example, the rectangular window. Rectangular window, so to take a block of fixed length L every time. So now we have a block of L points in the time domain, and we process them individually. Every time we process one block by going to the frequency domain using FFT. Okay. So now XK is in the frequency domain already. Okay, and as I will see, in general, we can perform certain manipulation in the frequency domain. There is an endless possibility. But in our next example, we're going to work in the frequency domain when y is equal to x times our Fourier transform of the impulse response. Multiplication in the frequency domain can be computed at every sectoral line k. Okay? K is from 0 to, let's say, the length of ft minus 1. Okay? Perform a length of n multiplication in the frequency domain. Sample-wise, multiplication in the frequency domain means what? Means convolution in the time domain. And that's FIR filter. FIR is convolution in the time domain. But we know that convolution in the time domain is equivalent to multiplication in the frequency domain. Right? So therefore, just simply by multiplying our spectrum with our transfer function, we get the output spectrum. We get one block of output. And then what's next? Just go back to the time domain. Okay? Go back to the time domain and put everything together. You have a signal in your output. And the computation load can be saved. Computation load is lower thanks to FFT. Thanks to FFT. Okay? It's going to be faster than performing direct convolution. Okay? So that's the kind of overall framework I want to share with you. So FIR filter, we know that. So here, the next slide is just a reminder that convolution in the time domain is equivalent to multiplication of spectrums in the frequency domain. And how that happens, back to this flow, is again, in the middle, when we obtain our input spectrum for one block of signal of length n, what you do in the frequency domain is just to multiply our spectrum with the FFT of our impulse response. Here, H is the impulse response. So seriously, what you can do here using the MATLAB notation, seriously, first, this is the result of your design. You should be proud of this. Okay? This is the FIR filter, low pass filter, the impulse response. Take the entire thing, which is finite length. Okay, finite length. Take it and then perform FFT of that impulse response, and save it to a vector h, which is the transfer function, which is the frequency response, saved in a vector. Now, next, perform sample-wise multiplication of your input spectrum with the Fourier transform of impulse response, and call the result y. So we are performing multiplication in the frequency domain right here, using MATLAB notation. Okay, and then from there, y is also a vector, right? Perform inverse Fourier transform to go back to the time domain here. So here you get a block of output, y0, y1, a block of output back in the time domain of a certain length. Okay, the final length might be y of n FFT, minus 1, transpose. So that's one block of output that we obtain. Then put everything back together, and that process is called overlap add. Okay, overlap add. The result, you're happily with your output by performing filtering in the frequency domain. Okay, filtering in the frequency domain means multiplication right here. This is a key step. Okay, it's the key steps. So in this homework, I have a question asking you to calculate the computation load for the entire process. Okay. Computation load meaning how many multiplications need to happen to finish processing your signal. Okay, so FFT. So there might be, you can say there might be. So the computation load might be n log 2n right here for every block, and again inverse transform is also n log 2n. Okay, roughly speaking. And how about here? Please do not forget that here, for every frequency sample, there needs to be a multiplication of our spectrum, input spectrum with the impulse response spectrum, right? So here's frequency-wise multiplication. Right here we have n multiplications. So the total number for processing one block might be what? N times 2 times log 2 of n plus 1, something like that, okay? You know that that's a computation load for processing one block of input. And you can compare that with direct convolution. And hopefully, direct convolution, you'll see that by an appropriate choice of n, we have acceleration right here. Okay? So I have a concrete example, in your next homework, the homework number 6. There's a question. Please take a look. If you do have enough time, you come back tomorrow for discussion. Okay, so that's in your homework. But so I'll leave it to you. This is one example. When you choose the FFT length, there's an important thing that you need to know. Okay. An important point is to choose the length of FFT. How do you choose it? Let's say, for example, okay. For example, if the block length is m, and the filter length, this is the order of your FIR filter. Turns out to be something, okay? So the recommendation is that you need to choose the FFT length that's larger than at least L plus m minus 1. please be aware of this. Okay? I'll explain why. Okay? The FFT length needs to be at least, I should say, greater than or equal to. Okay? Greater than or equal to L plus M minus 1. And usually we choose the power of 2. Okay? So in this case, the next smallest power of 2 is 1024. So that's a serious recommendation that we need to be aware of. And long story short, if you don't obey this, don't follow this recommendation, what could happen is time domain aliasing. Okay? Now, time domain aliasing. Okay? This is a bad example. If we choose the length of FFT to be simply m, which is smaller than L plus m minus 1, that's a bad choice. That's a bad choice. Okay? Why is it bad? Why is it bad? Because if the length of FFT is too small, then the output, when we perform FFT of x times FFT of h and the inverse FFT, the length is equal to 512. But that's not enough to describe the correct output. Because the correct output has a length of L plus m minus 1. Okay? The correct answer is convolution. And the correct answer for one block of output got to have a length. The length needs to be L plus m minus 1. Okay? So any FF length that's smaller than that will not do the job. Any length of FFT that's smaller than that does not do the job. This is incorrect. Okay? And the way it is incorrect is that the last part of the output is going to be wrapped around and superposed to the beginning, which is wrong. And we call this artifact, we call this way of doing things wrong, we call it time domain aliasing. Because now things are appearing at the wrong place in the time domain aliasing. Things occurring in the time domain at the wrong place. This is called time domain aliasing, wrong place. Okay? So quickly, the recommendation is that to use a length that's sufficiently long, such as 1024. So apology for using a few, maybe 10 more minutes, okay, before I entered this semester lecture. So the correct way is to set an FFT length that's higher than m plus L minus 1, okay, such as the power of 2, the next power of 2, 1024 in this case. Then what's going on is that we will require you to pad zeros, just to append zeros. Yeah. Now, block length is still 512, okay? This is 512. The block length is that, but then after that, just simply add zeros. Yeah. Add zeros, append zeros, 附带一些 zero. Append zero all the way to the end of your FFT length. And do the same thing for our filter. Our filter, really, the length is only 257. But after that, add zeros. Don't be too shy to do that. 不要太害羞. Don't be, just be confident. You just add zeros. It's stupid. It looks stupid. Lengthen your signal. Lengthen your block. But then perform FFT. Go to frequency domain. Go to frequency FFT. Use FFT to go to the frequency domain. And then simply multiply the spectrum right there in the frequency domain, and then perform I inverse FFT. That gives you the right answer. Now the answer is good. That gives you the right answer. Because we know that cyclic convolution will do the job. Okay, that gives you the right answer. Okay, so this is a tiny important detail that I want you to know, that when we follow that flow of filtering, performing filtering in the frequency domain, be certain that we choose the FFT length to be sufficiently long, longer than L plus m minus 1, so as to avoid time domain aliasing. Okay, so as to avoid time domain aliasing. Okay? So otherwise, we will just create one block of output after another block of output like that. First block of output, second block of output, third block of output. Then your final job is to superpose them. Okay? Put them all together by adding the overlap part. Okay? So notice that now the length of FFT is 1024, but the block length is 512. Block length is 512. So from one block to the next, there will be overlap. There will be overlap in between blocks. From one block to the next block, there will be a region of overlap. So the recommendation, and which is the correct way to do, is to simply add the overlapped parts. Okay? Simply add them, superpose them, add them. Okay? Add them in the overlap, you should be fine. Okay? And adding summation does not involve multiplication, so it does not significantly increase your computation load. Simply add the overlapped part. Okay? And this action is called overlap and add. Okay? For the name's sake. Just literally overlap and add. Now. All right. So I think I'd like to just simply just remind you of this final plot. Okay. Just to summarize, we begin with input, and we use a rectangular window to take the signal one block after another. So now, with each block, we go to the frequency domain, perform filtering by frequency-wise multiplication. That's a key point. Okay? And it turns out that after a certain analysis, you can show that this is going to be more efficient computationally. This is more efficient than performing direct convolution in the time domain. More efficient. Okay, that's the entire flow. That's the entire flow. So far, so good. That's the entire flow. Okay. And the semester is going to. My lecture is going to end in a few moments. So, yeah. So my last slide is kind of an overview of what we have learned for the entire semester. Okay, that's why I really want to talk about it. Right. This slide is kind of a summary for the entire semester. Okay. Okay, so. 这好像在说啊。So here I present an overall comparison of FIR versus IR filtering. 就学习有时候是会见树不见林啊。When we see like individual trees, we focus too much on individual trees in the forest. Sometimes we lose the overall picture. So that's why thank you for sticking with me till this final moment. I really want to share with you the overall picture of for the entire semester. What have we learned? We learned to design FIR and IR filters. Basically, that's all we learned for the entire semester. Okay. IR filters are difference equations. Nothing more, nothing less. Talk about IR filtering, you think of a difference equation with yn to your left-hand side equals to what? Summation, right? And when we go to the z domain, h of z equals to bz divided by a of z, right? That's all we learned. IR filters are difference equations. But what are FIR filters? FIR filters are also difference equations, but without feedback. Without feedback. Recall that those structures, right? FIR filter looks like a ladder, right? And that ladder ladder structure, right, does not have any feedback. But otherwise, you can say that FIR filters are also difference equations. Okay? You can call them difference equations, but without feedback. Okay? So they have a rather simplified structure. Okay? I want to share with you that in my practice, of more than 20 years, the order of FIR filters are often much higher than their IR counterpart under the same specifications. Same cutoff frequency, same transition width, same ripple requirements. Usually, you can find a IR filter with lower order at a lower order that will do the job. So that seems to imply that IR is a more efficient implementation. Okay, it appears to imply that IR leads to better computation efficiency. And when we look at the reason why FIR filters usually has a higher order, a long length, because we design them by window method. Okay, we're keeping the middle part of that low-pass filter impulse response, and the longer the merrier, right? Basically there's a trade-off. If you just truncate, you keep more of the central part, you can narrow the transition width. So the trade-off is right there, directly related to the duality of Fourier transform. Longer in the time domain, narrower in the frequency domain, right? Just because of the transition width, usually we need the FIR filter order to be, the order usually is something like 100, 200, even 500 in that order, depending on the requirement of transition width. Okay? So it seems that so far the advantage is for IRR is lower computation load, but we have mentioned that FIR has its own advantage of having constant group delay. How important is that? Maybe not so important, frankly. Is group delay a really important feature? Do we really want to ensure group delay being constant? So it's not really convincing. Yeah. But finally, thanks to FFT, okay? Thanks to FFT, now in this very lecture, this very last lecture, last part, we learn not to convolve in the time domain directly, but to go through the frequency domain through FFT. And FFT being FFT, F stands for fast, right? Because of its beautiful structure right there. Please recall those structure. Because it's a beautiful structure, turns out that it enables us to accelerate FIR filtering. Even though it looks strange that by doing convolution, we need to go to a frequency domain. It seems to a detour. It seems like a detour. 看起来像是在绕路。Seems like a detour. 看起来真的像是在绕路啊。Convolution is an operation in the time domain, right? By definition. But it turns out that thanks to FFT, we can go to a frequency domain and come back, and it still be faster. That's the beauty of this acceleration process that I want you to understand. Okay. So finally, computation load for FIR filtering, according to my experience, might be even lower than IIR. According to me, a log 2n. Log 2n is much smaller than n, if you notice. Okay, for a long filter, turns out that you can accelerate many times, simply because log 2n is much smaller than n. Okay, simply because of that. Okay, so FIR filter now might be the winner. Okay, it has constant group delay, and thanks to FFT, it can even be made faster than IIR. So so now the final question. Now, is there any drawback, any disadvantage of FIR? Now with FFT, it seems everything can be accelerated. But now the disadvantage here, I want to share with you, the disadvantage of FIR might be the memory. Because here, and latency, okay? Simply because we need to take one block of signal at a time. You got to use some memory space, okay? This operation requires some memory space, at least. You need to save the entire block first, before we even talk about processing, right? So there is a kind of higher requirement for data storage, at least temporarily. Store them in a register before we can even start processing the signal, okay? So the drawback here at IIR is one sample in, one sample out, okay? So the requirement for memory is there, and also latency. Also because you need to store one block first, we need to wait until the block enters. Then we can start processing as fast as we can, produce the output, and then put them back together in the time domain, okay? So there's always a time that you need to wait until one block comes in before you can start processing the next block. So memory and latency are two factors we need to consider. If you can bear with that, okay? If you can tolerate these requirements, then FIR might be your better choice. It's faster and linear phase, okay? And so otherwise, most FIR filters have an advantage of having a constant group delay. So that would conclude all my lectures right here, okay? Again, thank you for being here with me. That's it. That's it. Hopefully, I'll see you somewhere, sometime, on campus. Okay. See you. See you. I see you. See you later. 是吧？那个，now transition with longer. 答案是什么？ Now transition with longer filter. Okay. 好。So we will be back. I will be back. Okay. See you later, alligator. See you. 谢谢。下台鞠躬，谢谢。好，请说。